This is lab 4, magnetic braking with Faraday. So the purpose of this lab is to observe Faraday's law by dropping a magnet through a tube of aluminum foil. The experimental result was 1.24 seconds and the computational result was 1.16 seconds. The system is the magnet and the aluminum tube, and the surroundings is everything else. And so for the lab, we had to use the magnetometer app to find the north pole of the magnet and then set up an aluminum tube, and then drop the magnet through the tube while timing how long it takes to fall, and then repeat 4 more times for a total of 5 times. So some fundamental physics principle you need to know in this lab is the Biot-Savart law, Faraday's law, magnetic flux, magnetic force, and Newton's second and third laws. And some of the assumptions made in this lab is that air resistance is negligible, gravity and the magnetic force are the only two forces that are acting on the magnet, and the bar magnet acts as a magnetic dipole, and the aluminum foil models an aluminum tube. So this is the observations / data that was obtained. So the length of the tube was 0.3 meters, the width was 0.006 meters, the radius was 0.03 meters, and the inner radius was 0.02 meters. And the mu from lab 3 was 3.69, and the mass of the magnet was 0.025. And the average time that we got from the experiment was 1.24 seconds. So why can't we use like a steel pipe? This is because the magnet would stick to the side of the tube and would not end up falling through it. And then what happens to the magnet? How does it compare to a magnet falling in free space without a tube? There is a resistance against the magnet when falling, and if it fell in free space, it would fall more quickly. So this is the computational model. So the first picture on the top left is basically just sets the initial conditions, and then the pictures on the right is the first picture is the function for calculating the B field of a dipole or the magnet, and the second function is for calculating the change in flux. And then for this code, it calculates the force of gravity on the magnet, and then the current, the induced current on the ring, and then the magnetic field and magnetic force, and then the F net, and then it updates the velocity and position, and then this is the graph that the model produced. So some of the possible errors is that there might have been errors keeping track of the time it took for the magnet to fall, and the mu used in the code was actually greater than the mu that was found in lab 3, which meant that there could have been errors in lab 3 when we were finding the mu. So the intensity of the coloring on a tube indicates the magnet of the current flowing through each ring, and red and blue indicates opposite directions. So which color corresponds to the clockwise current? So red corresponds to the counterclockwise because you can know that from Lenz's law. And then if you flip the magnet around, the direction of the induced current would change, but everything else would stay the same. And then the total time in two of the real-world system compared to the computational model were pretty close, and it would have been more accurate if the tube was split into more rings. And then the shape of the velocity versus time graph is unbalanced in the beginning and then balanced when the magnet hits terminal velocity, and then at the end it becomes unbalanced again as it speeds up. So what if the conductor was reduced as close as possible to zero? There would be near zero resistance, which means that the induced current would be much greater, which causes a greater magnetic force, which makes the magnet fall more slowly. And then if there was holes or slots that were cut into the tube, then it would reduce the current flow and the magnet will fall through faster.